problem, meaning I have one gas in one of the bulbs and a second gas in another bulb. And I will say this, what's missing is that this is the methane. Oh yeah, it says partial pressure methane. Good. I was gonna say, you can't do this problem if you don't know which gas is which, but it says partial pressure of CH4, which is methane, is in one of these bulbs with a pressure of 3 atmospheres and a volume of 1.164 liters. There's a valve between them. In the other bulb, there's a partial pressure of oxygen. And what we're going to do is we're going to open the valve and allow these two to mix and react. And we're going to assume that they react to completion. And since we have a pressure and a volume of one species and a pressure and a volume of another, both at the same temperature, we'll be able to get moles of each of them, and this is a limiting reactant problem. And then the other thing that's going on here is that we are creating gases, and we're going to have to figure out the pressure of those gases as well, and then add them up to get the total pressure. So that's an overview of this problem. Let's go ahead and attack it. So for methane, we can find the moles of methane. I will do it a slightly different way this time. So I'm going to write my ideal gas law up here, PV equals nRT. And then since I'm looking for moles, I will rearrange it and personalize it for the moles of methane. Moles of methane are going to be partial pressure of methane times volume over RT. And a similar expression we'll do for oxygen in a minute. But now to find my moles of methane, I'm going to be partial pressure of methane times volume, which I've got both of those numbers right here. And I know my R, 0.08206, and I know my temperature, 383. I got my units here, liter atmospheres per mole Kelvin. Zoom in a little bit. And then I've got my temperature, 383 Kelvin. So my moles of methane, 3 times 1.164 divided by 0.08206 divided by 383. I get 0.111 moles of methane. And then I can do the same thing for oxygen. I know for oxygen, I have 38 atmospheres. I have a different volume, but my denominator is the same. So I'm just going to plug things in. I have 38 atmospheres times 0.827 liters divided by R and T. Then I get 0.9999, or let's just go with 1.00. Now these are moles of reactant, and I need to know both of my moles of product eventually. So it doesn't matter which one you choose at this point. I'm going to choose carbon dioxide, and I'm going to convert both of these into moles of carbon dioxide. Although perhaps you can see what's going to be our limiting reactant already. It's going to be my methane because it's a 1-to-2 ratio and I've got more than double my amount of oxygen. But again, so these kinds of hints are always useful, and they can they can guide you onto what work you need to do. But since this is the video that I'm going to be putting together for the homework, I'm going to do everything for this one. I know for every 1 mole of methane, I am going to create 1 mole of carbon dioxide. So my moles of carbon dioxide, if methane is my limiting reactant, are going to be the same number. Similarly, let's see here. Let's try and get as much on camera. There we go. Now for 2 moles oxygen, I produce 1 mole of carbon dioxide. Which would be 0.500 moles of carbon dioxide. That means that methane is my limiting reactant. And oxygen is in excess. We're going to say something else about this too, by the way. Since methane is our limiting reactant, the partial pressure of methane, since we ran out of methane, the partial pressure will be 0. And we still have to figure out what the partial pressure of our oxygen is. We still have to figure out what the partial pressure of our carbon dioxide is, since that's a gas. And we also have H2O gas. So we still have 3 gases to do. But one thing we can say for sure is there's no methane left over, so there's no pressure. Any questions so far? All right, let's zoom out a little bit. Okay, so things we need to do. We have our moles of CO2. Now let's find our moles of H2O gas. Always come back to the limiting reactant and the moles of limiting reactant to find how much of your product you can make. So let's go back here. So now we're going to find moles of H2O produced. And we're going to use our limiting reactant. This time, let me get that on screen. This time we know that for every 1 mole of methane, there will be 2 moles of H2O. So I just double those numbers that for moles of CH4. Next, I'm going to find my moles of oxygen left over. To do that, again, I have to come back to my limiting reactant, find out how many moles of my O2 are reacted away with it. And this step in particular is one that students more often forget than some of the other steps. There is a 2-to-1 stoichiometry here, so you have to account for that, which means that 0.222 moles of O2 are reacted away. And we know how many moles of O2 we started with. We know how many moles of O2 we reacted away, so we can find the moles of O2 left over. So, and I'm going to squinch this down here in the bottom here, 1.00 moles O2 start minus 0.222 moles of O2 reacted away equals, and I better call on my trusty calculator here. 0.778. And I will still keep 3 sig figs here, even though I know there's only 2 decimal places there. That's fine. Left over. Okay, so we're not done yet, but we know our moles of oxygen left over. We know our moles of H2O produced, and we know our moles of CO2 produced. And we know that there's no methane. We also know a couple other things, and I'm going to have to go to a second piece of paper, so let me note these, I guess, right here. So we know all our moles of products. We know that our temperature is 383 Kelvin. And we know that our volume, now that the valve is opened, is the total volume, which is going to be the 1.164 liters plus the 0.827 liters. And I don't have that number, so 1.991 or 1.99 to 3 sig figs. Okay, so the only thing left to do is to take each of our gases that are left over, which is our oxygen, our carbon dioxide, and our H2O, which are produced, plug them back into the ideal gas law to figure out their partial pressures, and then add them all up to get our total pressure. So here's what this looks like. Let's start with oxygen. And we're solving for pressure. So our partial pressure of oxygen is going to be moles of oxygen RT over volume. We know that our moles of oxygen is 0.778 moles. It's at this point that I've written R enough on this problem that I'm just going to write R and plug it in. And then our temperature is 383 Kelvin divided by 1.99 liters. Multiplying all this out, I get that my partial pressure of oxygen, 0.778 moles times 0.08206 times 383 divided by 1.99. And there's a dot in there. I get 12.3 atmospheres for the partial pressure of oxygen.
Excuse me, Professor.
Question, yes.
How did you get the mole of oxygen again?
How did I get the moles of oxygen? Good question. So from the previous one, so let me ask you a question. Are you comfortable with the fact, or do you have questions about the fact that methane is the limiting reactant and that O2 is in excess? Are you comfortable with that?
Yes.
Great. Okay. So we started with 1.00 moles of oxygen. So we start, then we found out using our limiting reactant how many moles of oxygen reacted away with our limiting reactant, and we found 0.222 moles. And then we just subtracted those two to find our moles of oxygen left over.
Oh, okay. Thank you.
Yeah, no, so that's a good question because that seems to be coming up in a lot of our questions. So it's a good step to understand. What's interesting about this particular one, or different from the previous problem that we solved for this homework, is that you do have to do the stoichiometry because it's 2 to 1. It's not just 1 to 1 like pH problems, like some of the pH problems. Okay, so let's see. Partial pressure of carbon dioxide is going to use the moles of carbon dioxide that we came up with before, which was 0.111. and everything else is the same. And what we get this time, 0.111 times 0.08206 times 383 divided by 1.99, 1.75 atmospheres. And then one more time for H2O. And for H2O, we previously solved for 0.222 moles of H2O, and everything else is the same. And in fact, since it doubled here from carbon dioxide to H2O, we could just double our answer. I always like to do it out. Well now, so, and it actually goes to 3.51 atmospheres, which we would have gotten 3.50 here. Either answer is fine for this problem because it will be within the tolerance when you enter it. And anyway, so last thing is to take all of our pressures, add them up to get the total pressure. And I get 12.3 plus 1.75 plus 3.51 and to 3 sig figs, 17.6 atmospheres. Though if you reported 4 for this one, that would have been fine too. So, and that problem did take almost, me, writing large though, almost 2 full pages to answer completely. So, that was quite a problem. Any questions? Any more questions about it?
Professor?
Yes?
Can you just go through the question real quick from like the beginning?
I sure can. So it says the apparatus below contains methane and oxygen at a temperature of 383 Kelvin. The valve in the center is opened, and the methane reacts with the oxygen. Here's the balanced reaction. Solve for the final pressures of all species and the final total pressure. So our process for doing this, maybe I'll just write about the process as I go now. So the first step was to determine the moles of reactants, or calculate. Calculate moles of reactants. And then 2, find limiting reactant. And when we found the limiting reactant, we went and did this green portion where we took and we did stoichiometry to moles of one of the products. So, all right, find limiting reactants by finding smallest moles of product. And then we found out that our moles of CO2, and we could have chosen H2O, but you could choose either one. My reason for choosing CO2 is it had a 1 coefficient, and I like 1s in my math. Sorry, it has a 1 coefficient. I like 1s in my math. All right, and then once we knew that the partial pressure of our CH4, which is our limiting reactant, equals 0. So partial pressure of limiting reactant must be 0. And the thing that, of course, is implicit or goes unsaid, I'm going to go ahead and say it, must be 0 after the reaction is completed. Like so. And then once we knew our limiting reactant, we had to find the moles of the other product. And that's right here with H2O. And so whenever you find the moles of the products, you have to use the limiting reactant. And then we had to find the moles of the O2 left over. Where O2 is our excess reactant. And so again, we return to our moles of our limiting reactant, do stoichiometry with a mole-to-mole conversion to find our moles of oxygen reacted away. Subtract that off the moles of O2 that we started with, and we'll get our moles of O2 left over. Everything good so far? Or you want me to keep going? You got any questions either way?
I'm good.
Cool.
I don't know about everyone else.
Yeah, no, everybody else can jump in anytime. All right, now we're on to page 2. And page 2, basically what we did, and I'll write this down in a second, but we basically took all of the stuff that was left over, all of the gases, and we figured out their partial pressures. So I guess I'm going to write find partial pressures of each gas present at the end of the reaction. Find partial pressures of each gas present at end of reaction. And I think you know this. We already said that it will not include the limiting reactant. And 6, finally, is just going to be add up the partial pressures to get the total pressure. And that's the step I'm showing right here, where my finger's pointing. Add up partial pressures to get total pressure. So that's taking it step by step. I will say that for this particular problem, everybody in the class will get different atmospheres of each of the gases, and I think there's like 50 different options. And sometimes oxygen is the limiting reactant, and sometimes methane is the limiting reactant. So everybody will get a slightly different problem to test, but the process is exactly what I just said. Calculate the moles of reactants, find the limiting reactant by finding smallest moles of product. The partial pressure of the limiting reactant is 0. Find moles of the other product that you didn't already find. Find the moles of oxygen. Find the partial and total pressures.